recommend writing notes.
1.4 is very similar to 1.3. Now, what do those mean? 1.3 talked about, section 1.3 in the book talks about segments, measuring segments. And in particular, it talks about the segment addition postulate. 1.4 is going to do some similar stuff, but for angles. It's going to take the same concepts that we dealt with previously in section 1.3, and it's just going to apply those to angles instead of segments. Okay? So before we jump into things here, I want you to remind me of something. The segment addition postulate says, if I have point B, which is between points A and C, and does that work? Does that picture work? No, are people shaking their heads? Is B between A and C? How come? They don't. It doesn't lie on the line connecting A and C, does it? Good. So I'd have to put the C maybe up there.
Yeah, right there.
Okay, and so now that looks a little better.
Yeah, it's still not a straight line.
It's pretty good though. Okay, so the segment addition postulate says if B lies between, quiet please, if B lies between points A and C, then what? AB
Equal or plus AC equals AB.
plus.
BC equals AC.
Okay, and what does it mean when I say AB like that? What I really should say is something slightly different. What I'm saying, yeah, okay, almost. It's not the segment. The segment AB I would write like this. Right, with a little bar, exactly.
Oh,
the symbol.
points? The point and all that?
So it is the points, but
Or
what about the
distance
points?
between the points.
Distance, good. We could say there's two ways we could say it that are equally good. We could say it's the length of segment AB, or we could, or the measure of segment AB, either or we could say it's the distance between A and B, okay, between points A and B. They mean the same thing, of course. The length of the segment connecting points A and B means the same thing as the distance between those points, right? Everybody agree? Okay. So we're talking about distances. The distance from A to B plus the distance from B to C equals the distance from A to C. Or the length of segment AB plus the length of segment BC equals the length of segment AC. Segment addition postulate. Good stuff. Okay, no big deal though. Now in 1.4 we're going to apply this kind of thinking to angles. But first we need to talk about angles a little bit. You know, what do they mean? How are they defined? What are the parts of an angle, etc. The angle symbol that we use is this in math. Now in Moodle, we don't have access to that symbol, so instead of that one, we use the next best thing, which is the less than symbol to mean angle. Okay, we define an angle as two rays that share the same endpoint or initial point, which we're going to end up calling the vertex of the angle. Okay, so here's an example of an angle, right? What would we call the vertex of that angle? What is it? Okay, so it's just point X, or X, right? If we break this into three parts, we've got the top side of the angle, we've got the vertex, and then we've got the bottom side of the angle. How could I label, or what would I call the top side of the angle? What do you suppose? YX. Okay, I mean that's a good start. It involves the points Y and X. That's true. We want to be a little more specific though. What kind of a thing is it? Not a point. It looks like more than a point. I'm starting here and I'm going out there forever. So what does that seem? Line, close. It's like a line, but a line goes forever, and this one stops at X. Now a line segment would stop at Y, but this keeps going. All good suggestions, but we're just almost there. Array. Sure. We'll call it a ray. Okay, with the sides we could say are rays X, Y, and XZ. Now this is important. If I want to, this is the way we mathematically write a ray. Could I say ray YX and mean the same thing? Because I could with a line, couldn't I? Line XY and line YX mean the same thing. But do ray XY and ray YX mean the same thing? No, they don't, do they? Because with a ray, there is a specific direction associated with it. This ray is starting at X, so the X has to go first, and then it travels through Y and on forever, right? So we need to call that XY and not YX. Make sense? And then the bottom one, of course, would just be ray x z. It's the bottom side of that angle. Now, another issue, how do we say that in Moodle? We can't write this symbol in Moodle, so how do we say it instead?
We put a little arrow next
Good, I mean, that's a good guess. We just do this. The word ray, and then in parentheses, we put the points that define the ray. Okay?
to it.
All right, so then we say point X, you already told me, is the vertex. Oops.
Hey, question.
Dots here.
Do you want us to put like a comma between the X and the Y, or?
No, you don't. Just put the letters next to each other. Good question. So the vertex is just X. Okay? Point X. And what do we name this thing? Okay, now, let me go back a little bit. You tell me, what do I name this angle? There's a bunch of ways I could name this thing. Somebody give me one name of this angle. Okay, X, Y, Z. Okay, because those are, I need to name it with 3 points maybe. Okay. Now, here's our scheme for naming angles. When we're naming an angle, you want to think of it as giving an ant directions how to turn the corner formed by the angle. Okay? So if I tell the ant, and I'm always going to start on one side, go through the corner, and then to the other side, right? So the point associated with the vertex always has to go in the middle. So if I say angle XYZ, I'm actually telling the ant to do this. Start at X, travel to Y and turn at Y and go through Z. Okay, so it's not quite what we wanted. We're very close. What would I say instead? YXZ. Good. Or ZXY. Yeah, those would both work. Okay. There's one other name we could also use, actually, in this case. There's a real simple one. We can call it X. But we got to be careful with that. Okay, I'll talk about that in a second. So, appropriate names would be angle YXZ, angle ZXY, or even angle X, but only if that's not confusing. Only if there's only one possible angle X. What if I had a situation like, well, and we just use the angle symbol in Moodle, for example. What if I had a situation, oh, and if there's a number in there, before I move on, I could call it angle 5 too. Sometimes we'll do that. We'll put a little number in there. Makes it easier to refer to the angle. Okay, what about this one? Now, I can't call any of these angles angle B. How come?
Because there's more than one.
There's more than one. We don't know which one we're talking about, right? There are 3 possible angles that I could call angle B here. I could be referring to that one, or I could be referring to that one, or the great big one, right? We don't know which one it is, and so as a consequence, we can't call it angle B. None of those could be called angle B because it's ambiguous. We don't know. Confusing. Angle measurement. Okay, this, if we put an M in front of an angle, that means the measure of the angle. In the same way, so measure of angle A refers to the number associated with angle A in the same way that the length of segment AB refers to the number associated with the segment AB, right? So an M in front means we're looking for a number. We're going to measure it in terms of what units for an angle? What would the units of an angle be?
Degrees.
Degrees, yeah. And there's some other ones we'll talk about later, not so much in this class. But for now, degrees. Okay. We measure angles with protractor, okay, and the units we use are degrees. Now here's an important word in geometry, congruent. Okay. We're going to talk an awful lot about this. We're just scratching the surface here at this point. Later on, this will be a much more important word for us. Let me have phones and stuff. Oh, wait, please. So congruent in geometry means same shape and size. Okay, so it's a word that we use to describe geometric things, not numbers. Congruent is used to describe stuff that I can draw on paper or I can point to, right? They're geometric things. So angles with the same measure are congruent because they're interchangeable. I could pick up one angle and set it down on top of another angle, and they would overlap perfectly if they're congruent, right? Now I'd say the measures of those angles, which are numbers, those are equal. But angles are not equal. Angles are things, they're not numbers. So angles would have to be congruent. Here's maybe a better example. if I draw, here, I'll do this so they look good this time. I've been doing this all day, and you never look very good. These will. Okay, that square and that square, even if I do this, are congruent. How come? Because they're the same size and shape. I could pick this guy up right here. I could turn him around and set him down on top of this one, and they would overlap perfectly, right? But the first square and the second square are not congruent if it looks like that. Because now they don't overlap. See what I'm saying? Oops. Make sense? Okay. So if the measures of the angles are equal, then the angles themselves are congruent, and this is the symbol that we use for congruence. Now we're not going to really be doing that at this point, but we'll talk more about how we do that in Moodle later when we get there. Okay, so new postulate, protractor postulate. Very simple. All this is saying is just like the ruler postulate said we can measure distances with a ruler, protractor postulate says we can measure angles with a protractor. So if we take a protractor like this and we line it up with an angle, so the vertex of the angle is sitting right on the little hole in the protractor, and let's say that one of the rays of the angle, one side of the angle lines up with the 20-degree mark on the protractor, and the other side of the angle lines up with the 55-degree mark on the protractor. How big is the angle? 35, sure, we just subtract, right? Just like we would with a ruler. And really we want to include the absolute value there because we could also subtract the 55 from the 20. And as long as we make sure our answer is positive, we're always going to get 35, right? But typically we just subtract the small number from the big number. We don't have to worry about it. Okay, more about the anatomy of an angle. Of those points up there, which B is where? In the interior or the exterior, do you suppose, of that angle? I hear a couple of both. Okay, what do you think now? Interior would mean inside. Exterior would mean outside. So it'd be interior, wouldn't it? It's on the inside of that angle, right? So B's on the interior. What about C? Exterior. That'd be the exterior. That's on the outside. Good. Now what about D? Ooh, I'm hearing both, or neither. It's actually neither of the two, because the interior would be all the points that are clearly on the inside of the angle.
Isn't that a trick question?
It is. It's a trick question. It's actually not interior or exterior. What would be a better answer, maybe?
On the line?
On the line, exactly. On the angle, we should say. D is on the angle, because it sits on one of the sides. Okay. What about A? What's that? Vertex, yeah. Okay, angle addition postulate, very simple. Now this PowerPoint is messed up though, I gotta fix this. I didn't notice this until I started using it. But the angle that we're talking about is angle QRS. So if point P is in the interior of angle QRS, like this, right? Then what the angle addition postulate tells us is that if I draw a ray that starts at R, pass it through P, I'm creating two other angles, aren't I? I'm creating this small angle here and this small angle here. Angle QRP and angle PRS. All the angle addition postulate says is that these two angles, because they're scrunched up against each other, we'd say they're adjacent angles. When we add them up, the measure of angle QRP, this angle, plus the measure of PRS, this angle, must equal QRS, the whole thing. That make sense? Yeah. Pretty straightforward. Now here's the kind of problem you're going to get with this. What if we're told that the measure of angle QRP is 5x, so here's QRP right there, right?
Yeah.
And the measure of angle PRS is 2x, and the measure of QRS, which is the whole thing, is 84. could I set up an equation to solve for x?
Oh, yeah.
Sure. What would I say? What would my equation be?
Well,
Yeah. You got it.
yeah, I'll put the stuff.
Okay, 5x plus 2x equals 84. So I can combine like terms and get 7x equals 84. Divide by 7, and what do I get? No? 12, yeah. X is 12. Now, more likely, I'm not looking for x. I'm probably looking for maybe the measures of the angles themselves. So how could I find the measure of angle QRP? Plug it in. Plug in 12 for x and get what? 60, yeah. So that guy would be 60, and this one would be 24, sure. Okay, good. All right, couple more, we're almost out of here. Types of angles, just some vocabulary. Remind me, what's an acute angle? Less than 90, good. Greater than 0, less than 90. Okay, so between 0 and 90. Looks something like that, maybe. What's a right angle? Exactly 90, good. Okay, so is that a right angle? How do you know?
Exactly, straight up.
Ah, okay, the drawing is, but this is a trick question again, I got you again. In geometry, we can't say, just because something looks like it's 90 degrees. Yep. Ah, good, okay, perfect. Just because it looks like it's 90 degrees doesn't mean that it is. Maybe I'm just a crappy artist, which you'll find that I am, and I didn't mean to draw it to look like a right angle, and I just did. Maybe it's not supposed to be, right? Or what if it's something like 89.997 degrees? Can you tell the difference between that and 90 by looking at a picture? No, you can't. So what we need is that guy. We need the right angle symbol, don't we? And then now that tells us, even if it doesn't look like a right angle, it is a right angle. Okay? What's an obtuse angle? Good. Greater than 90 and less than 180. So something like that. And then the last kind, what do I call an angle that is exactly 180 degrees?
Straight line.
Almost. I think I heard
Straight
it.
angle.
Straight angle. Good. Okay, good.
That shit.
Perfect. We say adjacent angles are angles that are next to each other, so they share a common side and a common vertex, like these guys do. Angles 1 and 2 are adjacent, right? Because they share the same vertex and the same side, but they have no common points on the interior. I want you to name some angles for me. There's a challenge here. Name an acute angles. Raise your hand, somebody. I want to get some. Yes, ma'am. Say it again. S. Oh, say it now. Say it again. Say it. You got the right angle, but you said it incorrectly. You're talking about this angle right here, but how do you have to name the angle? Not STB. Remember, I got it. The ant's got to start on one side. We got to tell him how to turn the corner. He's going to go from S, turn the corner at B, and go to T. So SBT is what you meant. Okay. What's another one? Yes, sir. TBC. Good. What's another one?
ABS.
No. ABS is a right angle. So we said the angles, but maybe a different name for one of those angles. Yes, sir. Scott. Angle 3 would work. Or angle 2. Those are all examples that would work. Okay. What is an obtuse angle? Yes, ma'am. Yeah. TBA, sure. Or ABT, yeah. That's good.
I thought you said like B.
Okay. Name a right angle, somebody.
Or ABS.
A right angle.
ABS. Number 1.
Yes, sir. Right back here. Straight.
Number 1.
ABS works. Give me another one.
Number 1.
Number 1. What's another one? Right here. SBC. Sure. Those all work. Good. Okay. Name a straight angle.
Wait, I got a question.
Okay, question right here. Yeah.
You know it's a square angle, but why don't they have a square on that side?
Okay, because if this is a straight line, then as we're going to talk about later, this whole thing is 180 degrees.
But maybe that's just a little
Okay.
more off.
Yeah, that's. I see your point.
Yeah, but then it's not.
Yeah, I know, maybe people made this into a
No, I get your point. Unless we're told differently, though, we can always assume that this is a straight line. Okay, that's a good question. Very good question. What's a straight angle?
ABC.
ABC. Good. Angle ABC. Very good. Okay, let's head on down. I think we're good.